Hey everyone, let's talk about something that seems super simple in C programming. How does a program actually end? You've got return, you've got exit. They seem kind of similar, right? Well, the difference between them is actually a rabbit hole that leads to some really fundamental concepts. Concepts that can literally make or break the security of your code. So let's dive in.
So let me just ask you this straight up. What really happens when a C function ends? You probably think you know the answer, and you're probably mostly right. But there's a subtle, crucial distinction that, believe me, trips up even really experienced developers. We all learn this on day one, right? The return statement. It wraps up what a function is doing and politely hands control right back to whoever called it. It's like the function saying, okay, I'm done, here's what you asked for, you're in charge again. This is pretty much the bedrock of how we build structured programs. But this is where our story takes a fun little twist. We've just laid out the simple, polite rule of return. Now, let's introduce a function that seems to come along and just shatter that rule. Let's talk about the exit function paradox.
See, it turns out there's this other way to end things, the exit function. But it doesn't just end one function, it brings the entire program to a screeching halt. Think of it less like leaving a room and more like hitting the big red game over button for the whole application.
And here's where it gets really weird. The official ISO C standard, the rulebook for C, says, and I quote, "The exit function cannot return to its caller." Now, wait a minute. That seems to completely break the fundamental rule we just talked about, doesn't it? How can a function just not return control?
So that brings us to the core puzzle here. If return is all about politely handing control back up the chain, why is exiting forbidden from doing the same thing? What makes it so special? It really feels like a contradiction. So, is it a contradiction? Actually, no, not at all. The answer is all about shifting our perspective. This is the big reveal, and it all comes down to understanding the massive difference between the world inside your program and the operating system that's running it. And this chart illustrates it perfectly. So look at return. Its scope is tiny. It's just inside the program. Its job is to transfer control from one function to another. It's an internal conversation. Now look at exit. Its scope is the entire program. Its action? It terminates the whole process by yelling out to the host environment, to the operating system itself. It's not talking to another function, it's talking to the boss. So the key insight, the real aha moment, is this. Think of return as a conversation happening inside your program. It's like one function passing a note to another in class. But exit, that's pulling the fire alarm. It's a final command to the operating system that sends everyone out of the building. A function can return, but at the end of the day, the program itself has to exit. Okay, so that's a cool little piece of trivia, right? A neat conceptual distinction. But why does this actually matter? Well, this is where theory slams into reality. Let's step into the danger zone, because getting this wrong can have some pretty serious real-world consequences. Because this isn't just some academic debate. Misunderstanding this boundary, especially the fact that a function's little world just disappears when it returns, can lead to some classic, really dangerous security flaws. And the experts over at the SCI's Cert C coding standard have a lot to say about this. And just so you know, the Cert C coding standard isn't some random style guide. It's a set of rules developed by experts at the Software Engineering Institute for one reason: to help people build safe, reliable, and secure systems. So when it points out a problem, we should probably listen up. And the rule that absolutely nails the issue we're talking about today is DCL30C, declare objects with appropriate storage durations. This is really all about an object's lifetime. How long is it guaranteed to actually exist in memory? Okay, take a look at this non-compliant code from the standard. The function initArray creates a local character array, maybe initializes it, and then it returns a pointer to that array. Seems simple enough, but can you spot the critical flaw? Here's the huge problem. That little array has what's called automatic storage. That's just a fancy way of saying it's temporary. It only exists for the lifetime of the function it's inside. The second that initArray function executes its return statement, poof, the memory space for array is wiped clean, it's gone. Which means the pointer we just returned is now pointing to, well, garbage. This, my friends, is the dreaded undefined behavior. And trust me, that's a phrase you never want to hear. Your program might crash, it might seem to work just fine, or, in the worst-case scenario, an attacker could use this dangling pointer to read sensitive data, or even execute their own malicious code. It's a massive security hole, and it all starts with a simple misunderstanding of what return actually does. So what's the right way to do it? Well, the compliance solution completely flips the logic. Instead of creating the array inside and passing a pointer out, we do the opposite. We create the array outside, in a safe place where it's going to stick around, and then we pass a pointer into the function for it to work on. The function does its job, returns, and everybody's happy because the memory is still valid.
Understanding this kind of distinction is what elevates you from just writing code that compiles to practicing true software craftsmanship. It's about seeing the bigger picture. At the end of the day, writing secure code isn't about memorizing 1,000 different rules. It's about understanding the whole system, the whole architecture. It's about knowing where the boundaries are, where the locks are, and where the keys are. It's about building something that you can actually trust. So if you take just one thing away from this today, let it be this. That boundary between your program's internal world and its host environment, the operating system, is absolutely fundamental. Return lives inside that boundary. Exit crosses it. And most importantly, when a function returns, its local world completely vanishes. Which leaves us with a final thought to take back to your own projects. Your code compiles. Great. But is it actually secure? After what we've just talked about, what little vulnerabilities might be hiding in plain sight right at the end of your very own functions?